if we look now at the integral 7, first thing we need to ask with these integrals is why is this integral improper? So you have two limits here, none of them is infinity, so if it is improper, it is of the second kind. There's no problem at 2, right? The logarithm of 2 is a finite number, and near 2 this behaves perfectly well, and so that's this one here. The only problem of the denominator is when t is equal to 1, because for t equal to 1, the denominator vanishes. The numerator also vanishes, so actually we don't really know whether this is an improper integral or not. Depends on where, what is the limit of this function here. But if we calculate this limit, because if it is well behaved, I mean if the limit when t goes to 1 of this function here is finite, then this integral behaves, I mean it's a proper Riemann integral, and there's no problem. We can, it's of course convergent. I mean there's no problem in calculating that. This would be a continuous function. So we need to analyze what happens when t goes to 1 on the right, because the interval we're working in is 1 to 2, right? So we have the logarithm of t here plus t minus 1, and down here we have t minus 1 to 3/2. Well, one thing we can do is we can apply L'Hopital, and I think applying L'Hopital is enough to realize that this integral diverges. This argument diverges. Because if we calculate L'Hopital, or we apply L'Hopital, this is 1 over t plus 1 here, right? And down here we have 3/2 t minus 1 to 1/2. Now there's no problem in the numerator goes to 2, right? However, the denominator goes to 0, which means that this integral, or this function here, diverges. And then, so that's this one. So this one diverges too, right? Okay, so now we know this integral here is improper of the second kind because the argument here is divergent. Right. One thing that you can always do is whenever you have an integral like this where that it has a singularity at a point which is not 0, like this one here, you can just shift the integral to 0. And you can do that by a simple translation of the argument. So you define x to be t minus 1. Of course, then the limits are 0 to 1, right? When t is 1, x is 0. When t is 2, x is 1, okay? And of course, the x is dt. No problem with that. Then what you have here is the logarithm of t, which is 1 plus x. And then you have t plus 1, which is just x. And down here you have x to 3/2. Right? And now we have the problem at 0. All right, but we know something about this function. So we need to figure out what is the behavior of this function near x equal to 0, right? But of course we do. We don't know what is the behavior of this function near 0, because we know that the logarithm of 1 plus x is equal to x plus ox when x goes to 0. All right, so we can substitute this here, and then we have 2x plus ox up here, and down here we have x to 3/2. We have 2x because we have x plus x, right? It's 2x. Okay, now we can divide by x the numerator and the denominator, and then we have 2 plus O1 divided by x 1/2. So actually, this function, let's call it f of x, this function f, and this is what we found here, behaves as 2 over x to 1/2 when x goes to 0. So the only integral we need to deal with is this one, the integral from 0 to 1 of dx over x 1/2. But we know that if we have this integral of this improper integral of the second kind, which is just, it is of the second kind because in the denominator there is a positive power of x, then if this exponent is smaller than 1, then the integral converges, and this is the case. The exponent here is smaller than 1, so this is a convergent integral, and then so is the original one. All right, so this integral converges.